We've seen, like with the last one and also some of the others, very beautiful examples of new possibilities using the spin. But sometimes I don't see how you can really scale, like you do it on an STM tip. And that's very beautiful for an experiment. But how can you scale things and make functional devices like that?
I mean, in that sense, I guess you could say we're confident that in the future we'll be able to eventually, there'll be it's more of a fabrication approach, I guess you could say. It's more of, will they be able to eventually scale down?
Someone else's problem.
Exactly, yeah. We're trying to understand is what happens at that store, so then eventually when we get there, we'll have something ready for you.
What I do, but it's like coming here to the engineers.
So I think, let me just comment, because I was a co-author on that work. The approach of doing the prototyping with FIB, so far we haven't been able to succeed to get data that we're confident is giving us a junction area less than 10 nanometers. But we are hopeful that by pushing on that and switching to, for example, helium ion versus the gallium ion beam, we should be able to at least make, let's say, monolithic devices, not relying on that trick of depositing the MTJ on a probe tip, and get data. But that's not a manufacturable technology, right? So to scale down to MTJ pillar size below 10 nanometers in a manufacturing environment, that is a major challenge, which is not addressed in this work. Did I see another hand? Eli, you want to jump in?
Well, I have only two. You know, I listened to all these presentations. Of course, I want a solution, and I want you to be successful. But with each of you, there is a drawback that I can detect. As let's say I would put on my hat and say, well, I've got to make a decision, maybe invest some money into one approach or the other approach, and try to figure out what could be successful. So the first thing that comes to mind is the presentation by Jimmy Zhu, and also by Dr. Shuto from the Tokyo Institute of Technology, where you're dealing with the problem of maybe not such a good on-off ratio, and that therefore you would have a lot of static power dissipation. But your solution is to use basically to switch the circuit off, let it rest, and that this would solve the problem of static power dissipation. Now, this goes against the way logic circuits really work, because they kind of don't always know when there's a signal coming in, and so they have to stand by. So then you add a silicon transistor standing by to switch off your magnetic switch, and I think there's a limitation in how well you can perform. I don't think it really solves the overall problem. And Jimmy, why don't I let you go first and try to respond to that?
Right. I think I think you are right to some extent in some applications, and you need a device to sense, whether I want to turn on this block or not turn on this block. But one thing of this is actually is whether you send, if you want this to compute, then you send the clock, and otherwise you don't send the clock. So you don't have to either wake up, or there's no wake up issue, things like that. Okay. So, but more important, I think it may have a use of in the energy intermittent environment. Suppose you have an energy harvesting device, and this energy comes and goes, and this is probably the best.
The problem is we can turn conventional silicon circuits. We can turn those on and off too.
Yeah, but in the energy, my understanding is in the energy intermittent environment, the silicon becomes really complicated.
Okay. Yeah, over here.
So I had a complex question about the steam wave array for pattern recognition. So you show that using this YIG, you can propagate waves very far, and you can build up this experiment, which is millimeter size, which is very convenient for experiment. But if you want to scale that down to have a very small chip, won't you have problems of coupling between your nanomagnets, and how can you go to smaller scales?
According to theory, there are some publications from other groups in Europe. We can go up to nanometer scale, like waveguides of 10 nanometers with small magnets, 10 nanometers sitting on them, and it still work. I mean, according to theory. And we just don't have these capabilities to make these small structures. It's very challenging for us.
Okay, so, okay, go ahead.
This is Rigar from Intel. When I see a couple of the devices, it's really interesting ideas, Dr. Khalili, for example. I look at it and I'm worried about the idea may work for one device, but when you have millions of hundreds of millions, setting a time, constant time, we know those devices have not just have the spatial variation, but temporal variation too, from switch to switch. It's a good idea, but I'll be worried about studying it further. The same question goes for Dr. Shuto, related to the SRAM idea, which is a great idea to have a non-volatile memory, but the restore operation. I wonder what happens if you have a real mismatch in SRAM, two sides, when you have real 100 millivolts of transistors at both sides, and if the idea works. So those are the worries when I see if the idea is good, but it will be nice if we can work on the effect of variation.
So why don't we have Pedram respond first?
Yeah, sure. I agree. I think that's a great point. And when you're talking about memory, it's not just one bit. You want billions of bits to work. So I sort of alluded to it in one of the slides. I didn't elaborate on it. But one of the things that's very important is to optimize the device in the free layer to have basically as wide a write window as possible where you have low write error rate, right? So that's not easy to do, but there is quite a bit that you can do. So if you just make a device and you measure, you may not even get to 100% switching probability, and it may be a very narrow window, but you can extend that to hundreds of picoseconds. But you're quite right. So I think we need more data for sure on actual arrays to be able to really see what the window is across large numbers of devices. So yeah.
Okay, so in the lack of matching issue for your non-volatile
Yes.
SRAM cell?
Yes, in our study, the SRAM has a very large 6 MOSFETs, but the MTJ is required for 2. So in recent technology, according to recent technology, the area size is larger. SRAM is larger than the MTJ, so the mismatch is not so hard for, compared with the MRAM. MRAM has the one MTJ, one transistor. So, but in future, this problem occurs in our study. So so I think in the future this problem. Yeah.
Okay. All right. So in the remaining time, I have a provocative challenge for all of the speakers. In putting together this session, I'm particularly happy that we got a really good range of the different applications for Spintronics. So we heard a couple of talks about basically using Spintronics for memory, a couple of the novel memory applications, or let's say technology implementations for Spintronic devices for essentially pure memory. We heard about magnetic logic, using Spintronics to try to get very low voltage operation and non-volatile logic. We heard about an even more advanced type of concept for a pattern matching type of system using wave properties in spin wave properties for pattern matching. So, and one of my favorites is the introduction of non-volatility into CMOS circuits as a way of reducing standby leakage power in CMOS circuits by using the non-volatility. Again, kind of a unique application of spintronic memory. So we see a variety of different ways of applying Spintronics towards energy efficient information technology. So what I would like to do is, I know all the speakers are quite expert in a variety of aspects of spintronic technologies beyond the work you are doing on your own particular favorite style. So I'm going to ask each of the speakers to draw on your deeper knowledge of spintronics and make some positive comments about one of the other technologies, the ones that you're not working on, so that we can get a little bit of a sense of how these technologies are compared, not by having the advocate for each one talk only about their technology, but I'd like for you to advocate for one of the other applications, and we'll start maybe with Jimmy.
I think STT-MRAM, that has a really good prospect, and because the industry is really pushing it, and the thing is, if you have a significant research effort and some challenge like distribution, which is when you get to, you want to get an error rate of 10 to minus 9, 10 to minus 10, and that's, you need a lot of engineering work, right? But the industry is sort of determined to make it work, and especially for like embedded technology, and you really will add some significant advantage to the embedded technology with the MRAM can be directly put on top of silicon, right? And so I think that prospect is pretty good.
Pedram?
Yeah, so I would maybe like to advocate maybe for, or basically say a few positive words about combining CMOS with magnetic power junction. So I think the idea that you can really dramatically reduce standby power dissipation is important, and it's becoming possible even with maybe relatively low densities of memory to do interesting things, which I think is important because getting to very large densities of MRAM at the moment I think is difficult, partly because of the TMR. If you want to make many gigabytes of MRAM on a chip, it's very difficult because of basically, especially at scale nodes where resistance variations are larger and so on. So I think it's important in the sense that it may enable new things and it may motivate further work before I think some of the more advanced kinds of devices like Jimmy talked about, which are entirely magnetic, become a reality, which I think is also possible and eventually may very well happen.
Yeah. Let me just comment before we go on. I think we learned a really interesting message that we got from Nikolich's talk this morning that I think is relevant here, and that is as we introduce on the smaller scale some of these technologies, then the learning and the ramping really helps to refine the distributions, the manufacturing, the material quality, and some of these more advanced applications I think can then build on that.
Same things.
Alex, would you like to take a crack at this?
I would like to add that I think this idea of voltage-controlled magnetism or switching is a very promising idea in terms of power consumption. As of today, we have two types of, I have two examples. For example, synthetic multiferroics, when we have piezoelectric and magnetostrictive material. In this case, you have to apply just 1 megavolt per meter in order to rotate magnetization. If you calculate how much energy, it's very low energy. What today Pedram presented to us is you have to apply 1 gigavolt per meter. It's a little bit better, higher. But there is a trade-off. What Pedram presented today, you can make really small structures. With multiferroics, it's very limited. You cannot scale it down. Right. But I believe that one way or another, it will be very useful.
Very good.
I think the spin logic is a very important technology. So because in the almost the spin device is the operation voltage is become very low. So for the energy efficiency, the spin logic is important. But I think the one question, one difficulty is that the peripheral circuits still maybe CMOS, so in the future, I hope the all spin logic, all spin processor become is very important. So.
Thank you. Mark?
I guess I would further reiterate the first speaker in terms of embedding both Spintronics with CMOS technology. Seems to be the next natural step versus having a fully universal, non-volatile memory device. So I guess embedding them together and having clever power gating schemes to minimize whatever energy losses, I think is honestly probably the best way to go.
Okay. So now that we've had a little bit more ecumenical discussion about the different technologies, I invite any further comment or question from the audience. If Eli wants to say one more thing.
So there were in this five voters, and 2 people voted for voltage-controlled logic. Okay, well, you voted in your talk, and you seconded it. Okay, and I think there's a problem, and that is that you drive wires. The wires have an impedance of about 2 kiloohms or thereabouts, and so the only way to reduce the energy is to actually reduce the voltage considerably. So to say that you're okay because you have a high voltage, it's over a volt, but you're going to have very low current, that doesn't do it. It has to actually have be very sensitive. It actually has to have a low voltage. So I'm not buying.
So I should clarify. So first of all, when we talk about low power, I'm talking in the memory world. So that's still much larger numbers that people are used to than talking about logic. So for voltage-controlled logic, you're quite right. So basically the kind of voltages we talk about are way too large. Even for memory, it's probably still too large. But basically purely from power dissipation point of view, you can reduce the voltage or you can reduce the current, right? And so just having a more resistive device can reduce the ohmic power dissipation. You might counter then that, of course, because you're reading resistances in order to basically find out what's in the memory, then if you cannot drive large currents through it, it may be difficult to read, which is right. So you have basically you pay a penalty in terms of the read speed if you increase the resistances. But still, based on everything we've seen and circuit designers tell us, is that you can still get fairly competitive reading speeds even with the resistances that we're looking at least.
The problem is not the device resistance. The problem is the wire resistance. You have to get to the device through a wire. And unfortunately, the wires have a lot of capacitance. And so it ends up the only way to deal with that is to lower the voltage. And so if all you ever think about is the device, you're really missing where I think in general you're right, but if you actually look at the numbers, and we have designs for arrays of many megabits at least, so we basically we're not yet, as far as we can tell, gated by the interconnect resistance, partly because the resistance of these devices is much larger than that. But in general, I think you're quite right, and basically just looking at the performance of one device is never going to do it. It's really what
I think the considerations for resistance and right voltage and current for a memory array are somewhat different than for logic. So I think Pedram has a point there. But let me wrap up and make give my opinion maybe on this. I think Eli actually did make a good point in response to Jimmy's talk that power gating as a means for dealing with the high standby current of a low MR ratio magnetic device is a difficult thing, because if to be the most effective, you have to know which devices to switch off. So you want to switch off all the devices that are not active in a given clock cycle, and only switch on the ones that are going to have a signal that comes that requires them to switch. That's a very challenging thing to do. If you have a very high activity factor circuit like an FFT, like the one that you guys demonstrated, then this problem is less serious. If you're trying to design, random logic, it's much more challenging. That's why I think for magnetic logic, some of the most promising thing we can do is, again, take a lesson from our speakers in the morning session. Architecture is really a key. If we can figure out how to design architectures which are less sensitive to this need to figure out, or maybe more adaptable to this need to figure out which devices are switching when, we can probably make better progress on magnetic logic. So I think we should leave it there. Lunch is ready. We have lunch just out in the lobby here, is that correct? So let's just thank the panel and all the speakers one more time. I think it was a good session.